Okay, these are the check your understanding problems for 5.6 and 7, which is about concavity and second derivative test. All right, so for the first one, we're given a function and we want to know on which interval or intervals is f concave down, okay? So we know from our relationship that f is concave down when f double prime is negative. So I need to find my second derivative and then do a test on the number line to figure out where that is positive, or in this case, we want negative. So f prime is 3x squared minus 6x. F double prime is 6x minus 6. I'm going to set that equal to 0. I can divide everything by 6, so I have x minus 1 equals 0, meaning x equals 1 is the critical point on f prime, okay, because it's where f double prime is equal to 0. And then I can do test points around 1 on the number line. I'm taking values to the left and the right of 1, and I'm plugging them back into my second derivative, which is this right here, okay? Actually, I shouldn't put an equal sign there. I'm just going to put an arrow. Okay, so anything to the left of 1 is going to give me a negative. Anything to the right is going to give me a positive. Again, I'm looking at my second derivative, which I can look at this one right here or that one where I divided by 6 because I don't change the signs. All right, so where are we concave down? We are concave down when x is less than 1. So f is concave down on negative infinity to 1, open interval here. Okay, we always want open for concavity. And our reason is because f double prime is less than 0. Once again, that is all that we need. We do not need to have any, when this happens, then this is true, or when, like, we don't need any of the, like, conditional stuff. We just take the conclusion that came from this particular problem on this interval and say that's our reason, okay? That looks a little funny. I'm going to move those closer. There we go. Okay, and so that is complete. All right, number 2, second derivative is already given. It is already factored. Don't try and expand it and multiply that together and then realize you have to go back and factor it again. Just, it's already factored. And the question says, for what values do we have a point of inflection? So a point of inflection is going to happen when the second derivative changes signs. So again, our second derivative is already factored. Okay, just going to rewrite this down here so I can kind of write on it. If I set that equal to 0, I get critical points at 3, -4, and 6. Okay, I want to know where my second derivative is going to change signs. Excuse me. And I can do a full number line analysis here if I want, like a sign chart, but really what I want to notice is that this factor x minus 3 is being squared. The other two have a multiplicity of 1, okay? Or in other words, they're not raised to any powers. So really, just from my, pre-calc knowledge, I know that if I move from the left to the right of 3, from x equals 3, this factor is not going to change signs. If I move from the left to the right of -4, this factor will change signs. If I move from the left to the right of 6, this factor will change signs. So that tells me that these two are going to be the only two where my second derivative is changing signs. If you want to write that out, like if you want to do a full number line sign chart here, make sure you've got them in the right order. Okay, anything to the left of -4 is going to make, and this is always positive because it's squared, and then negative times negative, so that will give us a positive product. If I move to the other side of -4, like I said, this factor will change signs, but the other two stay the same. If I move to the other side of 3, I'm not going to change signs because of the square. In other words, something in between 3 and 6, I'm going to have a positive, and a negative, so this stays negative. And then to the right of 6, this last factor changes signs, and I have positive, positive, positive. Okay, so what do we see? Once again, the only places where our second derivative is changing signs is at x equals -4 and 6. Okay, so G has a point of inflection at x equals -4 and 6 because, and how do we know that? Because our second derivative changed signs, because G double prime changed signs. Okay, that's an ED. I mean, you could write out the word change too, but that's also fine. All right. Okay, number 3, here we have a graph of f of x, and we want to give the interval, probably going to be in terms of a, b, c, and d, where the first derivative is positive and the second derivative is negative. Okay, first derivative positive, this tells us that f is going to be increasing. Second derivative negative, this tells us that f is going to be, forgot the c, concave down. So I'm just looking at my intervals a to b, b to c, and c to d, and I want to know where is the function increasing but concave down. Okay, here we are increasing but the slope is increasing, so this would be concave up, so it's not that. Here we are decreasing and concave down, so it's going to be this interval right here. So the interval, for b to c. Once again, I'm using open intervals to be safe. Okay, and then the last one here, we have a table of values. We do know it's twice differentiable, so no issues with the second derivative not existing anywhere except where it tells us that f prime is undefined. And it says values are given. We are looking for any relative extrema. Okay, so this is our second derivative test. The second derivative test it's not repeating the first derivative test to find points of inflection like what we did up on number 2. Okay, that's not the second derivative test. The second derivative test still finds relative extrema, a relative max or min, okay? But the process is slightly different. So the first thing we do, and again, our instructions are up here, is we find our critical points of f, so the places where f prime is equal to 0, and then we are going to evaluate the value or the sign of the second derivative at these critical points. So where does our first derivative equal 0? And it's happening right here and right here. Now, this says undefined. Could I have a max or a min at a place where my first derivative is undefined? I can, so I am going to think about this one, but we'll talk about that in just a second when we get there. All right. So at x equals -1, my first derivative is 0. My second derivative is negative. That means I have a horizontal tangent and I have a concave down function. That means I have a max. Okay, so f has a max at x equals -1 because f prime of -1 equals 0 and f double prime is -1 is less than 0. Okay, and then also right here at x equals 3, my first derivative is 0, so I have a horizontal tangent, but my second derivative is positive. That means that we are concave up, so we have a minimum. So f has a min at x equals 3 because f prime of 3 equals 0 and f double prime of 3 is positive. If you want to say by second derivative test, you can, but we don't have to. Okay, let's look at what's happening at x equals 7. My first derivative is undefined. Once again, we can have a max or a min when the first derivative is undefined. However, second derivative test isn't going to be very helpful here, especially because our second derivative is equal to 0. Because I can have, like, let's say I have something like this. I'm going from concave up to concave up, and my first derivative is undefined, but that's not really helpful. So it's not conclusive by the second derivative test. And here, even if we said, okay, and the second derivative wouldn't exist. I'm trying to think of an example where we do have, where the first derivative is undefined, but the second is not. Nothing is coming to mind. There might not be, if there is a way, I can think about that more later, but if there is a way for the first derivative to be undefined and the second derivative to be either positive or negative, like for the concavity to tell us something, then the second derivative test is still not going to be conclusive, so we cannot get that from the information in the table. We would need something else. I'll keep thinking about that, see if I can come up with one, but anything where the first derivative is undefined, we're not using second derivative test. So that's it.